Good day to you. This is Anagalactic with our second presentation in a new series in which I intend to document the production of a paper. This is a phase of science that every, I'll just say, real serious scientist looks forward to if it can be achieved. The attempt to publish a new discovery. Now, many of the discoveries in science that are published, going back a long ways, are simply improvements on some system, but it is a legitimate discovery if it needs to be in the common storehouse of knowledge. So there are all kinds of discoveries, thousands really, and each year there are several more in various fields of science. Now this is geometry, in which there aren't as often new discoveries, although I suppose you would find out the full extent of that by a full exploration of geometry. Now, I have attempted to do that. Over the past a little over a decade, I've been concentrating on spherical geometry. And I have gone into detail in some of my previous videos on how I got into spherical geometry. Why was I doing it? It's always important to ask yourself why you're doing science, whatever part you're in. It helps one orient, so you remember your purpose. So in our case, I was not looking for a new geometry. What I was looking for was a method of spherical coordinate system transformation, which involves spherical rotations. So I was intimately involved with it. I'll just say at least 5 forms of known conversion methods for performing a spherical rotation, which is quite an interesting prospect. It's well known, or we wouldn't have space travel, so this is in the common store of knowledge. How to do a spherical transformation, which is a rotation. Now, what we're doing today is expanding on the previous video, which was released earlier today, in which the outline you see here was presented. Now, this is an expanded version of that, and just so you see where we're going, so you'll have an overview of what this intends to present. On this page, you'll see 6 bulleted items under line geometry, which is also called Euclidean geometry. And this is just a recapitulation of the formulation of systematic linear space, which begins with Euclid's definition of the 0D null point. The line is, of course, 1D, which indicates this is linear spatial separation. I use that shorthand, and I'm sorry if I'm forcing you to learn it, but I'll always spell it out. It just helps me write faster. So linear spatial separation is what the 1D line is used for. The squared plane, also called the Cartesian plane, although it has several names, is an extension of the 1D space. It's formally called a space. It's interesting, in 0D, it's an absence of any space, which is a problem, both for the number 0 and for the geometric 0D point, which is the frame of reference for all linear systems, 1 through 4D or even higher. They all have a 0 at the center, and that 0 is the numeric representation of no space at all, or anything else. It's a placeholder. So in the squared plane, we use 2 lines, and this is the beginning of extrinsic geometry. The line really, you could say, has a primitive geometry, and we're going to discuss that today briefly, although I have several lectures on that. It's quite important to understand the axiomatic formulation of linear systematic space, which we're taking up to 4D because that's where science is at now. But the squared plane was really invented, I guess it's somewhat debatable who invented it, but it's been ascribed to René Descartes, who of course popularized it. So it's called the Cartesian plane for that reason. It's a conjugation of his name. Cartesian is from Descartes. So that's 2D extrinsic. Now in the previous video, I explained rather, not in inordinate detail, but I'm pointing out a very important difference in geometric systematology or systematization. All geometry that's ever been used from Euclid to the present is extrinsic geometry. And what that means is that you're imposing a grid. And that's really all it means, so that's a perfect definition of linear geometry. It is extrinsic because it's an open grid. It has no closure. All lines go to infinity by definition. In order to get distance, you have to cut off two ends to get a line segment. So that is essentially the nature of systematic space, which extends 1D to 2, 3, and 4 quite systematically. So it is consistent, but it does need to be examined at its axiomatic basis. That 0D null point is now a serious problem, and it always has been. So 0 is a peculiar and troublesome pseudonumber, as I characterize it. Now, going forward to cubed space, that's what everybody calls 3D space, just rolls off the tongue. Well, whenever we refer to space, we refer to 3D space. Well, when you do, you're not referring to space. You're referring to the grid. That's why it's extrinsic. And the reason we use this grid, both in the plane and in volume space, is in order to get a coordinate fix. In 2D, you need two linear numbers to get a fix. If that's used to get a fix on a circle, you run into a tremendous problem, which the Greeks gave up on. But Newton did not. Okay. So in cubed space, we use three lines, one of which is necessarily invisible to us. And therefore, whenever we represent 3D in a projection down onto a page or blackboard, you have to tilt it. For the same reason you have to tilt a circular projection of, for instance, a spherical Earth, you have to tilt it in order to get an impression of 3D. Otherwise, you just draw a straight line across the circle, and that's supposed to represent the entire equator of a sphere. Well, you can't really get a visual clue that that's the case, except with practice. But if you tilt it, you have to remember to move the North Pole down. You can't have a stick sticking out at the North and South Pole if the equator curves. Because if it's curving, that means that the globe is tilted. And usually we tilt the northern hemisphere toward us just a touch to bring out the curvature that is the visual clue that that is a spherical equator, not a straight line through a circle, although they are related. But when I say one of the dimensions in volume space is invisible, that refers to the fact that we see a flat image, and we need visual clues in order to see depth. But then with practice, that becomes automatic, as you know. But we do have two forms of vision. This has actually been substantiated. I don't know if I could say proved, that we do utilize two forms of vision, but what we see is a flat screen. That's why a computer screen or a movie screen is so convincing that it looks real. It's because we see a flat screen image in everyday life, as well as on the computer screen or movie screen. So jumping to bulleted item number 4, that's 4D. I say time-space, but you most commonly hear space-time. They are equivalent, although there's actually a mathematical difference between the two. Both have been used, but space-time is now the conventional use. It depends on the signature of the 4-component number. That's just to summarize that. If you wish me to expand on anything that I say, leave a comment. I'll be most happy to do so. The 5th bulleted item is going a little past our systematic extension of linear systematic space to discuss something that comes toward the beginning. And here's where we're at, the quantum of linear spatial separation. Now, quantum has several, I'll just say, uses, contextual meanings that vary subtly from one use to another. So quantum is a versatile word in the way it has been employed in its developed usage in science. So quantum is somewhat of it's an ambiguous term for the reason that I just stated. If that's a substantial statement, I find it to be so. You may have a preferred definition of quantum, and so you know what it means. But I wish to point out that what you know of your definition of quantum will be contextual. And so I want to point out what I would call the best axiomatic beginning for the use of the word at all is, where does the quantum appear? Have we known of the quantum before quantum mechanics was developed? I would say yes. But of course the word quantum, I don't believe, was ever used in scientific literature until after, I believe it was Einstein who first used the word quantum. He used the quantum of, basically the quantum of light energy transmission, which was an extension of Max Planck's discovery, but Max Planck didn't call his discovery the discovery of a quantum anything. It was Einstein who first used that, you could say, a prefixual characterization word. So it's a quantum something. It's really a quantum of something. But what does the word actually mean? That's a tricky question, which Wikipedia has an excellent systematic method for addressing ambiguous terms. It will have a page called the disambiguation page, where it'll give you links to various aspects of your word, how it's been employed. Because you might mean quantum something, but you don't find it right away. Wikipedia will assist you with that, and it should have your option in one of the links, and you can jump to that page. So what I'm talking about is what I consider to be the original definition. This could be said to be retrospective, or what I prefer to say is it's explicative. How, even without using the word quantum, did we use the concept? Oh, yes. And so the basic idea of the quantum, it's most often presented when someone tries to do what I'm doing to explain the meaning of the word quantum. They'll begin with the Latin meaning. And it's quite simple. It's the same word from which we get quantity. So a quantum is a singular form of quantization. So the quantum refers to quantization. Quantization of what? Well, that's a very interesting question. Quantization of what? So that's what gives it its versatility. Is you're saying what? You're saying the smallest quantity in the system. So that is the quantum of the system. It's the smallest quantity in the metric. Now, in the case of the line, the way the line is used is for linear spatial separation. And that's why I call it the quantum of separation. It's the quantum of linear spatial separation. Every single word is critical, because you don't want it to be mixed up with the modern notion that's used in quantum mechanics, because literally nobody has yet figured out what that even means, although I have. So I know, but that is where we're going. That will be the subject of my 3 papers. Now, that aspect of my discovery will not be discussed in the first paper, which will simply be to present the geometry. You are now seeing my approach to formulating my document, and I will document every single step and every single word until I'm done with a paper that I publish. And so you'll see it first, within a few days, I trust. Now, what do I mean then by the quantum of LSS? It is the jump from 0 to 1, because that's the smallest spatial separation. Now that 1 is now ambiguous. It's a quantum jump from 0 to 1. Well, what's in between? Nothing is. Unless you measure it. So measurement is critical for a quantum. A quantum is something that can be measured. Well, that's what makes the quantum paradox in the quantum mechanical system so infuriating and frustrating, is nobody knows what's being measured. I do, though. And that's what we're getting to. It's difficult for me to decide at this moment, and I've mulled this over, how much of my discovery sequence I should reveal in one sitting, so to speak, or in one paper. I do intend to extend this somewhat so that you see where this is going for the second and third paper, which will be, if I get my way, it will be quite impressive. All right, but the first document sets the stage, and I believe it's the most impressive stuff of all in context, because it's an extension of our notion of geometry to intrinsic geometry. Everything you see on this page composes extrinsic linear geometry, which is redundant. All right, and then I put in here discussions. We will return to that because it refers to the Archimedean, the index, and the metric of the space. This is linear space, but I will be applying it to circular space. So that's where we're going. Now here we just have a little bit more. This is an expansion of the previous version of this document in the previous lecture. I've added a few things, but essentially you're seeing much of the same. I haven't erased anything, I've just added to it. So the circle is the other line, which is, I guess, I have to compromise somewhere in expressing, is the circle a line? Well, it is because you can draw it. That would be one definition of a line. But it's not a linear line. It's not straight. Well, then can you call it a line? You can, then you should. But it's a closed line. So that's where we're going. Planar geometry is the encompassing or class name for the geometry in which the circle occurs because it's a planar object. We say 2D, but now we have to stop saying that because we're not going to use the Cartesian grid. We're going to replace it with something else. In context, I should mention that this has been done before to a certain extent on a radar screen. I don't know how it's done now, but I would assume it's similar. You don't use a grid. Oh, I should say you don't use a linear grid. Although it's linearized, it would have to be or you couldn't get a distance measurement. But all the lines come out of the center because you're trying to get a fix on something on a flat plane on your monitor. It represents a position in spherical space if you're trying to lock on it to recover or blow up something. But in a radar system, it doesn't use a Cartesian grid. It uses what's called a polar grid, which is concentric circles. Now that's what we're going to end up with. But instead of it being an extrinsic grid, it's just a different kind of grid that uses circles for one of its aspects. Or you could even say dimension, although that word needs to be disambiguated. So there are more than one kind of grid, but in linear geometry, the grid is the reference frame. It doesn't directly represent the space, unless you're just working with triangles. You get doing triangulation. Well, that's why the right angle law is so important. It was named after Pythagoras, but its real name is the right angle law. The basis of linear algebra is orthogonality. So that gives us the option to use algebra, which we've mastered, I would have to say. And of course, it's linear algebra. So the second bulleted item underneath planar geometry is the closed planar curve. Now that's the circle. This is the Cartesian plane that's imposed on what might be construed as circular space. But nobody's ever thought of that, or they've been unable to surmount the difficulties in trying to make that numeric. It has to be numeric. And in fact, it has to be linear numeric, which involves a transformation. You may be aware of this from complexity, the complex plane. We're getting to that. It's a little further down. So let's jump ahead to save some time. I'm trying to be coherent and concise at the same time. Quite an art. So the intrinsic planar geometry is a surface geometry because it's intrinsic. There is no such thing right now, except in this paper I discovered intrinsic planar geometry. That's what I discovered. It is circular geometry without an extrinsic grid, which is quite different. It's a surface geometry. It's the geometry of the circumference, either of a circle or a sphere, and we will discuss the difference between a circle and a sphere because it's a strict mathematical difference. There is a definable formula for the permanent relationship between the circle and the sphere. They're virtually one thing, and our vision proves that. The sphere is obviously, well, quite a bit larger than the circle. Well, you can say exactly how much larger it is. So we'll get to that. So this is a surface geometry, the first ever surface geometry. And that has a name you can look up in Wikipedia under spherical geometry, then do a page search for intrinsic. And it will give you a very little bit of information with no real links, because it doesn't exist. Although some men use the word because they have what I would call a facsimile of the need for intrinsic geometry is known. It's just nobody's ever figured out how to do it. I did. All right, and then we'll get to the curious, most curious concept of angle. Angle is our current factotum or facsimile or just placeholder for intrinsic geometry, because an angle is something that you don't treat it linearly, it rotates. So you rotate a full circular angle, could be said to be tau, or 2 pi is what it is. It's about 6.28, just a little bit more, because it's irrational. Well, that's the problem. It's irrational. With respect to the radius, which is how you get the linearity into the circular system, well, that is exactly what we don't want. Because of the nature of linear space, it always has a zero reference frame. It turns out that the universe is unaware of that. The universe does not have a zero reference frame. You might say the universe does not have a reference frame. You could say that you could try to prove that by pointing out that everything is uniform in all direction to infinity. That implies that there's no frame of reference, because everywhere you are is virtually the center. Well, that doesn't make sense. So we have not figured out the geometry of the universe yet. I have. And that'll be in the second and third paper, but not in the first paper. That's an extension. That's an extrapolation from this new geometry, which is rich in discovery vectors, as I'll show in the third paper. But in the first paper, you're looking at what's going to go into it. Now, the computation of angle has to do, of course, with a circle. An angle always refers to a curve. There's not an angle in linear space, except orthogonality. But anything beyond orthogonality itself involves the concept of angle, which has to do with you're rotating the line to get a measurement on the circle. That is the definition of an angle when it's applied to the circle. It can also be applied to hyperbolic space, and there are other usages for other curves. But for the simple curve, the circle, the angle is measured in, generally speaking, it's measured as a function of the radius. We don't want that, although you can't avoid it because they are related. They're related on the number 6.28, which is tau, which is 2 pi. Now, complexification is the first employment of two-component number space. And it's very strange because the x-axis has the typical linear parameterization. It's our simple number line. But the vertical line is not composed on the same basis. It's in units of the square root of -1, which is very strange because that's a different metric, obviously. So there are two different metrics being combined. They're combined in a special way with a special function which does work. And that process of combining two numbers into one number is called complexification. And the power of this is so mighty that in cutting-edge physics, no other number system is in use. Only complex numbers are used. That, by the way, is a sign of failure. I solved that. The second means that we've used to get at angle is calculization, which I may have invented that word, but it is a legitimate conjugation of calculus. Calculization, it was invented essentially by two men, and it's a good thing that two men got this simultaneously, because they each got 1/2 of the definition, and that split has never been resolved. The calculus is an extraordinarily bad tool. It's highly misleading. So the calculus, although it has enormous power for engineering, is almost useless for rational science because it's a cheat, and I'll show you that. So that should end our discussion today. This is the original document, at least one part of it. Well, actually, have I gotten to this yet? I'm not. Oh my goodness, there's more to go. Well, we might want to save that. There's quite a bit here. Might want to take a look at this. How much time have we used? I want to just consult my clock here. Let me get over there so I can see it. Well, that's a half an hour. I usually like to stop at a half an hour, but I also hate to break continuity. So I'm going to go on. If you wish to take a break or turn this off and come back, this would be a logical place to do so. I can't. I really can't. I need to maintain continuity. So, the item number 3, which follows from the circle and the line. There's the line geometry. This is an introduction to the circle geometry, which then gives us the option for an intrinsic geometry. Why? Because it's a surface geometry. So, okay, so let's expand on that. You see why I like to maintain continuity. The parametric circular plane. What I mean by that is we're not using the Cartesian grid. We're not using a grid. Now you may say, how are we going to measure anything? We're coming to that, but that's where the human mind has been balked. I figured out how to do this. So I'm the first man to see this. And believe me, I've been checking for it's been 3 years since I made this discovery. So it's high time I publish, but I'll tell you the truth of why I haven't published. I thought I would have been publishing a year or even 2 years ago, but I was on so many discovery vectors. This just opens up physics to understanding it. It's remarkable what this geometry performs for us. An intrinsic geometry no one ever saw. All right, so it's high time we used it because it answers virtually everything, and I know that's grandiose, but it's time for that. I need to get someone to read this. Well, you're ahead of the game. You're with the guy writing this and documenting his composition process, which I'm sure is going to be valuable. It's certainly going to be valuable for me because it helps me organize my thoughts, and I know I have a source that I'm composing as I go. So it's very much helping me. I hope it helps you too. I'm sure it will. If you can endure the seeming inevitable delay till we get to the climax. There are several climaxes to come, which you won't want to miss. I know I sound like an entertainment to introduce, and our next guest is, if we ever get around to him. So the parametric circular plane begins with what we already know, the unit radius circle. Now that's usually called the unit circle but now we need two terms, and you'll see why. The unit radius circle is the method of getting at intrinsic geometry using an extrinsic grid. And the way you do that is with the radius, because that's a line segment. So you measure the line segment and say that it's 1. It's very important. That's actually a quantum number. It is the number we use for a quantum anything, but the units are important. This is linear spatial separation units. That's the metric of linear space, is linear spatial separation, LSS, yes. So that is how we compose a unit circle. And what does that mean? It means that the circumference now has a number, but it's an irrational number. Now what we want is to rationalize the surface, which would be to the quantum number, but it's not the linear one. It's a two-component one. It would have to be, obviously, because it's in two-component linear space. All right? Think about that. Let me say that again. Any line can only have one number to get the quantity out of it. You're getting a quantity out of a line. Well, that's linear spatial separation quantity, the lowest of which is 0 to 1, which raises a huge paradox. What's in between 0 and 1? That's the quantum paradox. So now you know what the quantum paradox is, perhaps most easily stated. And I've attempted, and I still intend, to compose a list of all the definitions of the quantum paradox. I believe I've counted between 12 and 16. So this is a monumentally pervasive problem. The quantum mechanical paradox, the problem can be seen in the term. It's not mechanical. So quantum mechanics is a contradiction. It actually should be called quantum dynamics, and I'll show you why. Mechanics has to do with sequencing, but dynamics has to do with balance. It has to do with force, and we're getting to that. You'll see the name Boshkovich at the bottom of the page here. We're getting there. Let's go. So we have two different ways, we're saying, to parameterize the circle. If it's the unit circle, then the circumference is an irrational number tau, which, remember, tau is simply 2 pi. That's the unitization of 2 pi, because you don't want the 2. You're having the actual number. There's historical reasons for that, which I've gone into, but it's not really that important. You can use either number. They're equivalent. 2 pi and tau are the same. But tau is correct. 2 pi is incorrect. It's inferior. You should say tau. A movement was generated at the beginning of the 21st century by a consortium of mathematicians around the world who published a paper saying we should change to tau. Well, of course, they knew that wasn't going to happen, but they are still right. It's just that science no longer has a feedback mechanism. And there are several reasons for, like, well, we'd love to, you're right, but we still can't. That is true. It can't be changed now. But it should be. It just can't be. Well, get used to that. That's basically, that's the paradox of superposition. All right, so bulleted item number 3, two-componency plane. Now, the plane is a two-componency space. This is the geometric use of the word space. So the space is no longer 1D. It's now 2D. So any position in the plane using the linear extrinsic coordinate system, the grid, has to be 2 numbers. And you already know that, so I'm not going to explain it. That would be a bit puerile. But if you have any questions, don't hesitate to leave a comment, because I will answer your question until you get a satisfactory answer and you say, whoa, okay, I got it now. And don't worry, I promise. Don't be shy. You never be afraid to ask questions in science. It's really the whole point, okay? All right, so what is two-componency space? Can we say anything about it right away to make it more understandable? Well, the plane is already two-componency space, so that's actually nothing new. But if it's extrinsic, then you need two numbers to represent a position. What we want is just one number. And that's a strange thing to say. How could you even do that? Well, first of all, you have to understand the difference between intrinsic and extrinsic geometry. Extrinsic geometry, that is the grid, the Cartesian grid for two-component space, you have no choice but to invent something like sine and cosine to get a representation on the circle. That may or may not make perfect sense. I hope it helps, but I think I said it right. There's an inside to the circle and an outside. There's no such thing in linear systematic space. There is no conception of inside or outside. If you have any questions about that, you may want to watch the previous video. Now, parameterization is a term I think that frightens people. I've learned to embrace it because it's really, there's no synonym for it. So what is it? It's the application of numbers to either a space or an object. When you say you parameterize the circle, which is what we're trying to say, you're defining the circle using numbers. Now, the way that that's done exclusively today is with sine, cosine. That certainly has served us, but it's a concession to the linear system, which is forced if you begin with a grid. You have to somehow average the vertical and horizontal aspects to get a concept of curvature, because it's going through two linear dimensions at the same time. So you need the calculus, and you also need complexity. And sine cosine is a form of complexity because it's a combination of two numbers. Now, those two numbers, using the Pythagorean theorem, can be added to one. But you see the problem with that. Both numbers in sine cosine on the unit circle are less than 1, and then they have to be converted using what's called the conjugation function to get the imaginary numbers back into linear space. So I hope that makes sense, but I'm pretty sure I said that correctly. Remember, this is formal. I have to be precise here, but I also don't want to in any way confuse, confound, or frustrate you. This is a first pass, by the way. I will be continuing to use these videos and adding to them. As you know, videos can be spliced and then used in another video. So I'm hoping a lot of this will be of permanent value and reusable in a reusable form. Now, the next item is inversive geometry, which is really a stepping stone, which I found incredibly enlightening. And it actually led me toward my discovery. Circular inversion is a well-known system, but it's not known to have any real purpose, although it does have one very good application. And you can find out more about inversive geometry from a man from the 19th century who is said to have discovered it, although it's sometimes difficult to say who discovered something. But J. Steiner, that is Jakob Steiner, I got his book and I read it, and I actually did his constructions, which are marvelously instructive, although tedious to someone of my lack of aptitude with instruments. Some scientists, well, sometimes you have to get your hands dirty. I certainly did with Jakob Steiner. I actually got a compass with an ink, to use ink, because I just saw someone else use an ink compass, and I just had to have it. So I worked out a lot of this stuff in Steiner's book. And the modern proponent of inversive circular geometry is Zvezdalina Stankova from Bulgaria, one of my heroines. And we'll come back to her, but that's where you can find out more about circular inversion. It's a geometry. And it's quite profound, although nobody's noticed why it's profound except I did. Now, this next item is the dyadic numbers. Don't let these terms confuse you. I'll explain them all. Dyadic numbers are essentially binary. It's the binary number system, but you see, binary, you can say it extends to the less than 1 fractions, But if you want to be precise, when you're including the less than 1 fractions, like 1/2, 1/4, and 1/8 all the way to infinitesimality, when it goes in both directions towards infinitesimality and infinity, those are the dyadic numbers. And the positive ones are the greater than 1 the greater than 1 dyadic numbers, which are 2, 4, 8, 16, etc. Those are the binary numbers. But the terms are more or less interchangeable. They're virtually the same thing, but there's a nuance that's missing from binary. It could be, you might say, misconstrued. Are you including the less than 1 fractions or not? If you explicitly want to include those, as computers must, you're talking about the dyadic numbers. But it's called the binary number system. They're synonymous, as long as you include the less than 1 fractions. Now, number systems in general are very interesting. And just to give you a rough idea or remind you of what you already know about numbers, they are used for different purposes. The counting numbers are the original numbers. They begin at 1 and there is no 0. And it simply goes up by steps called you know what that's called, right? By the index. So the jump from 0 to 1 is the same as from 1 to 2, 2 to 3, 3 to 4 is the same jump. These are all jumps. The number line cannot be continuous or you wouldn't have numbers. So numerization of an object is quantization. You have to have an index of quantization. That is called the quantum of the system. So the quantum of the counting numbers is 1. It's also the quantum of linear spatial separation. But in order to do that, it's no longer counting, it's distance. And for that you need 0. You do not need 0 to count. You may want to think about that and figure out if what I just said is reasonable. It could be debated, but I know which side I represent, and so I would defend my side. But there are 2 sides to that. All right. Down here we have the famous name, John Horton Conway. He died in 2020 of the COVID virus. A tremendous loss. That man was an amazing man in many ways, one of my heroes. And he is the discoverer of the number system definition for our linear number system. He finally defined what is a linear number. But here's the amazing thing. He included all of the infinities. And that's quite a trick. He used what's called transfinite, I believe it's called transfinite recursion. Well, no, it's not called that, but that's what it is. It's a transfinite extension of linear logic in order to make the jump, the necessary jump to infinity. There are an infinity of infinities on the number line. He proved that. And he showed a way to prove that, and that's one of the most amazing discoveries in the history of mathematics. It went completely unnoticed, except by a man at Stanford who's still kicking. His name is Donald Knuth. So there's a little background to what did Conway discover? Why is that so significant? It has to do with his formulation of the prototypical 0, which he proved has to be a split 0, and that was already known, but nobody was able to prove what it meant. Because on a computer, there are 2 zeros. And that's what causes the division by 0 error. Okay, without going into that in extraordinary detail, you can research any of this if you wish, or leave a comment, and I'll be able to help. So what did Conway discover? It has to do, first of all, with his split 0, what's called the meta step, which is part of an axiomatic sequence where he began at the beginning, it would have to be 0, and proved that it's a split 0. That is enormous, enormously profound. But only I seem to know why. All right. The other aspect of his surreal number tree, which is a binary definition of the linear number system, it begins with days of creation, and this is his term. Conway said these are days of creation. And day 0, which a mathematician can get away with that, day 0 is the definition of 0. And using just two rules, although there are footnotes, just two simple rules, he's able to derive, first of all, the entire counting number system from day 1, where the double 0 splits to plus minus 1. That's polarity. And then the next split, which is dictated by the two rules, it splits both on the negative and positive side. Now you have 4. You see, it goes from 0, 0, which is one number, to plus 1, minus 1, which are now the two branches of the tree. I'm pointing down. You can do it either up or down, but it splits. It's a binary split to 1 and negative 1, which is the definition of polarity. And then for my purposes, I just discard the negative side because it's a mirror image of the positive side. It just has a different polaric symbol in front of it, either plus or minus. But you can forget about the minus side. Of course it's there, and that is profound. But for distance, we only use the positive side. So distance is strictly positive. It's measured from 0 in the positive direction to get a distance. So that's the most important branch. But then what is 1 split into? According to the two rules, you could even say it's one rule. But it's 1, 2, or 3, or 4 rules, but it's really one rule, but it requires a little bit more complexification, which is not an evil term. But it's hard to say and just say one rule, but you could. So what happens with the split on 1? It splits to 2 over 1 and 1 over 2. You may recognize that as the relationship between frequency and wavelength. That is the quantum relationship between frequency and wavelength. The middle number for that space, which is a physical space. Now we're talking about physics. The wavelength and the frequency are related. And you can see that because whenever you multiply the frequency and wavelength together, you always get the same number, which, by the way, is the unitization of light speed. So it's highly profound that Conway discovered this split on day 1 to day 2. So what happens is you get a split number system for the line, plus 1 and minus 1. Those are the two quanta of the line seen going in two polaric directions. But on day 2, the two numbers split into 1/2 and 2 over 1. And that is the simplest relationship that can be conceived on the relationship between frequency and wavelength, which defines light speed. All of this is enormously profound and instructive, but you may not see fully yet what that implies. That is my job, is to show you what that means for physics. So now we move on to spheric dynamic space. And what does that mean? It's not mechanical. In other words, we're not talking about sequencing, which is like 1, 2, 3, 4 is sequencing. That's mechanical, because those are steps. But in dynamic space, you're talking about a permanent relationship. So it's more of a geometric concept than a mechanical concept. So dynamics fits right into intrinsic geometry, as I'll be showing you. Now this we just covered, I mentioned this. That's quantum relativity. The relationship between lambda... Oh, actually, that shouldn't be lambda. That should be nu. Let's see if I can change that here. I believe I have this programmed. Nu, does it? Oh, there we go. And that should be increased in size to match. So there it's nu, which is the Greek symbol used for wavelength. So the relationship between wavelength, the highest of which is 1/2, and frequency, the lowest of which is 2, those multiply to light speed, and that is the quantum of spacetime. Although we'll show you that it's not spacetime. That was actually an error. It's energy space. It's space energy, not space time. That's a major discovery which I made. So, again, grandiose, but it all fits. Now, the second bulleted item is Botchkovicic, or Botchkovician, infinitesimal space. Botchkovich worked in the 18th century. Around 1745, he published one of the greatest works of physical geometry ever published. And I have his book in 2 editions, and I also read it online. I didn't discover Botchkovich until 1 year into my presentation of my new geometry. My discovery, personal discovery of Botchkovich's work, changed the game and extended. That's when I knew that I probably wasn't going to publish right away, because Botchkovich has uncorked the genie's bottle. He saw what I've proved can be seen. All right, that's grandiose, but again, I have to do this. It's time. Now, hyperspheric GEM space, what do I mean by that? That's the furthest reach I have reached thus far with this geometry. Hyperspheric simply means the equivalent of spacetime. It's not hypercubic, though, which in order to get curvature, you have to use hypercalculus, which Einstein invented. So that's Einstein's discovery, was hypercalculus. In order to work a spherical function into hypercubic grid space, it's extrinsic, which is why it has a flaw, a major flaw. So when I say hyperspheric, that's the extension of the sphere into its next highest dimension, which clearly is invisible. That is imaginary. But by extending the sphere properly, that is geometrically with a sound mathematical basis, you can solve for infinity. Because there are 2 infinities in spherical space, which are conjugal. I think you're starting to see some connections. The first bulleted item under hyperspheric space, which is simply spheric space closed against infinity. It's a finitization of infinite space. It's also a finitization of infinite quantization. It solves for both problems simultaneously. That too is profound. Now, radiative electroforce, I'm trying to be presumptuous here, because this is dead serious and it's important to use the right words. But radiative electroforce may not make much sense to you. What it is centrifugal force. Electromagnetic radiation is the only known centrifugal force in the universe. And therefore you know what this next one is. Contractive magnetoforce. There's only one centripetal force in the universe. And there are 2 particles that represent radiative electroforce and contractive magnetoforce. Those are respectively the electron and the proton. The proton is the only spatial particle. And then rationalizations, that would be a bit much right now, to go into the rationalization of infinity and the rationalization of Imaginarity. I solved, both for the calculus and for complexity, so that you will not need either one ever again. You will also never need to worry about division by 0. It does not exist. I invented a closed number system. The linear number system is not closed at 2 ends. At 0, it's not closed. And at infinity, all of them, it's not closed. But spheric space is closed. Finite, complete, consistent, coherent, computable, and miraculous. And that ends our presentation for today. This is the second in a series of presentations to document my formal paper which will be released, I presume, if everything goes well and according to my present schedule, it will be by the equinox, but I'm post-dating it. I'll say it'll be formally presented on April Fool's Day this year, 2025. Thank you for tuning in. I'm sorry I get a bit emotional. This is a lot of work went into this, and it's important for me to be sure someone at least looks. So thank you for looking. Sorry. I really am emotionally elliptical, but thank God I've given up beer again for a while. So I'm doing all right. And the financial crisis, you may have noticed me mentioning it, I was actually in a terrifically bad situation for most of 2025. But now, the foreseeable future, there will be tuna for the cat. Actually, she eats crunchies now. It's cheaper and she likes it more. Amazing. So keep looking up. We'll have a lot more. Please stay tuned. It means a lot to me. Thank you.